Anything? John's been a long-time member, 50-year member of LIMARC. And we'll give you everything you need to know about grounding. John?
I'll give you everything you need to know to get started learning about grounding. It's very kind of a simple concept, but the execution is where it usually gets messed up. This way, I can turn it down to my next slide. Key points for the grounding versus bonding. So the two different functions, they can be used together, they can be used separately. They perform two different functions, but they're both very integral to providing a safe environment. Function of grounding and bonding, lighting protection, and that can be a whole study in itself. There's a lot of if you want to protect against direct lightning stroke, you're talking megawatts. Broadcast stations do it because they have multi-megawatts at risk. The amateur station generally doesn't, but what we want to do is prevent damage to your equipment and damage to your house. And there are code requirements for amateur radio stations, in addition to this general code requirements for electrical safety. Just a couple of definitions. Okay, ground, this means conductor path to the earth. Ground is connected to the ground. Bonding is to establish electrical connectivity and continuity between two more pieces of equipment. You can have equipment bonded together, but they're not grounded. You can have equipment that's grounded and not bonded, but typically you'll have equipment that's bonded and grounded to the desired single ground, and we'll get into that. The functions, bulk stabilization is primarily a utility issue to provide better regulation to the customer. It can be done two ways. Some of the European countries do the voltage stabilization at the user location. It's very involved. Providing an earth ground and referencing that in this country and many other countries. You want to provide an effective ground fault. You want to be able to have a path that if there is a fault, the current that's measured is enough to trip out any protective devices for the overcurrent. Lightning protection, again, generally amateur radio operators protect your equipment against indirect strikes or nearby strikes. A direct strike will generally do much more damage unless you invest a lot of money. Okay, what won't the grounding do? Won't prevent electrocution. Ground fault protection will protect against electrocution for ground faults. So if you're standing on a concrete floor and you touch the live wire, if you have a ground fault, circuit interrupter, it's going to trip and you'll feel it, you'll get a tingle, something more than a tingle, but it won't kill you. Okay, and electrocution does many times you see it in an article in the news where so-and-so was electrocuted doing this, he's recovering nicely. No, electrocution is fatal, it's dead. That's what it is. Okay? Some of the codes, there are state codes. The New York State was starting using the 2017 National Electrical Code, PA 70. The New York City, people who are in one of the 5 boroughs, they have their own code, which basically takes the NEC and then adds and subtracts things. They have a base 2011, which is the latest New York City code, based on the 2008 National Electrical Code, and then separate addendums, again, the size of the original. And there are local codes. Some of the local towns have codes, electrical installations, which may or may not specifically address dam stations as the National Electrical Code does.
The codes at the county level?
What?
County level?
Not on some stuff. You know, it's Suffolk has requirements for, county requirements for the licensing of electricians, but each town has their own particular requirements. Okay, the important materials, electrodes, conductors, terminations, especially remember terminations, you can have the best setup if you use the wrong clamp, the wrong termination, you defeat the whole purpose. I've seen people with thousands of dollars invested in towers and antennas, and then they put the ground conductor off with a hose clamp against the blade of the tower. That's not an acceptable way to make a connection. Okay, the goal is equal potential bonding. Want to make all equipment rise and fall at the same time. If you're going to have certain circumstances and elevating of the potential to a fall, but as long as everything's the same, the difference between them is zero, just like the birds on the wire. They're so close together, they don't feel any difference. Okay, single point ground, and again, it doesn't mean you have to hold one back to the surface ground in the house, but if there's anything within the same physical area of the contact, or where it can be connected via cable or anything else, should be bonded to the same ground reference. Now, basically, this is kind of crude, but so this would represent an area. Maybe it could be a room, it could be part of a room where you have equipment. It could be your radio equipment, computer, copier, fax machine, whatever you have that can either physically make contact or again be interconnected. Human tolerance to electric current varies based on weight. Charles Dalzell did a lot of people hold a cup with rice, and they would pass current through their body, and measure varies like sensation, slight pain, greater pain, and hopefully not get to the point where it's straight on. There's the NOLA. This is the tabulation of the different. Some of the measurements you made, but this shows a little better. You can see the overlap down in this range here, depending on the weight. So maybe just a tickle for one person means a severe shock to someone else. So that's why if you notice GFCIs, let's say GFCIs, they have either the receptacle type or the breaker type. They have said it should between 4 and 6 millimeters. Tell us that range where you get most of the overlap. This is the different faults. You can have lighting in a power line. You can have the primary come down on top of the secondary distribution to across. You get a surge coming through. So there's many sources of voltage that can create a problem, ultimately resulting in the ground potential rise. Outside, of course, the antenna, grounding bonding, power, buildings, especially the metal buildings that are adjacent to, say, a tower. You want to have them bonded together and will be grounded so that you don't get a flash over. And metal objects, fences can be a little tricky because if it's close enough, you want to bond to it, but you have to keep in mind at the far end that fence is going to be the same ground potential rise when there's a fall. So you may have to, in that case, put a rigid ground to level out the gradient, so there's no shock out of it. And then the key, the end and all, is the grounding field. Rods, plates, and so forth. All of the wiring coming into your structure has to be protected. Even unless you have 100% dielectric fiber, a lot of fiber has metallic reinforcement that can still provide a pathway. So again, you don't want to feed all your protection by having one line coming in that's not protected. The easiest way To do that, we have this inter-system bonding device where you can, clamp around your, grounding electrode that goes from the service line to the ground rod, and then you can tie in all of the system, phone, cable, and the light. So now everything is referenced back to the circuit, and that's very important, because now in the shack, you can have equipment with 3-wire cord many times. That green wire is going to be at the same potential as the service ground. If you have a coax coming in from a tower, and there's no bonding between them, if there's a fault, there's going to be a potential difference between the two grounds. Although sometimes that potential difference doesn't have a lot of energy, it can cause a arcing momentarily, and ions in the air and the equipment, and if it's nearby to another, like the power connections, it can create a path for the power pole. So you want everything at the same potential. Okay, ground electrodes and conductors form the key part of the system. Flat conductors versus ground conductors. Flat conductors have a theoretical benefit in most cases, but in most cases you don't achieve it because people try to use it without having the proper termination that makes to the flat conductor, or they bend it, increase it, defeats the whole purpose of having a lower impedance path. If you do go with a flat conductor, you have to be very careful in how you install it. You have to use the right terminations. It's easier to properly install the ground system with a cable type connection than a conventional conductor. And you have the clamps, different means of attachment, and you have welding. Welding could be conventional welding, but generally is exothermic welding, and it refers to as CAD weld. That's a trade name for one of them, but it's very effective. So one means of joining conductors that the NEC recognizes as the same as a continuous piece of copper. Their connections are everything. And you want to, again, everything should be grounded and bonded together and before it enters the structure. You want to keep the bad stuff out, don't let it get inside. The simplest thing is the ground rod, you have the connector, and the electrode, and the conductor that goes back to your, if this was a service ground, you would go to the panel. If it was to be a tower, you use the power legs. If it's the entrance where you have all the cables coming into your house, you may have a panel with a bus bar connected to the ground system there, have all the other individual grounding devices, and then that gets tied to the service ground and bonded together. In the ground electrode, you have these picture like shells of electric going out. So the closer you get together, now they don't infringe on each other's area, so you don't get the same effect. The code requires 6-foot separation. Typically, what you want is, twice the length of the rod separation. So for 8-foot rod, you really want them 16 feet apart to get the maximum benefit of the electrodes. Just the business installation. Number one is just from a physical point of view, having that like that. Someone's going to stick themselves on that. This sharp bend. This is something you want to avoid. When you do have any kind of fall, it's a very fast lifetime event. If you have anything that adds to the impedance of that path, it's going to defeat the purpose of the system. Sharp bends. All grounding conductors show gently, curve. You don't want any right angle bends. People will do it thinking look neat, but if the feet don't work, should have a flash over your generally at that point. The rods, this is really typical electrode that we deal with, there are other ones we'll just zip through it. Minimum 8 feet, actual buried in soil contact. So if 8 foot rod, you can't have 6 inches sticking above ground, it has to be buried down. If 10 foot rod, you can have some sticking up. The 10 foot rods, when they're used for lightning detection systems, has to be completely in contact with the earth. They can be installed vertically, horizontally, it's horizontal, that's between 8 feet. And it can be angled at up to 45 degrees. Again, the code only requires 6 feet separation, but twice the rod is preferred. New programs, concrete, enclosed electrodes, basically, if you have, say, a footing, and you have, one of several types of conductive material, the rebar, and copper wire, and so forth, if it's, surrounded by at least 2 inches thickness of concrete, and there's no polyfoam beta barrier, using rebar that's not epoxy coated, you can use this as your ground electrode. It's quite effective because concrete is a very good conductor. And that way we have a fairly reliable path that won't change that much. The volume choices. Interestingly enough, if you're using a rebar, and the rebar is just they have 2 blends spliced together, tied with rebar ties, that's still considered by the code as a suitable means for the overall connection because it's enough, the proximity is enough of this wall that it will get the current flow. Main thing is not you can't use a epoxy coated rebar for the ground. Other ground electrodes is through underground water pipes. Has to be at least 10 foot earth contact, and if you're connecting to it inside a structure, it has to be 5 feet or less from the point of entry. And this is primarily to avoid someone picking up a connection to a metallic water pipe somewhere in the house where there's some plastic pipe in between, which obviously will feed your grounding. Okay, metal building frames, if you like industrial, commercial type buildings. There are requirements that can that sometimes if you're in an apartment building and it's steel frame, if it meets these requirements in that steel frame connection can be used as your ground barracks. Other than the code provides for all electrodes, hyper conduit, 3/4 inches or more. Can be stainless, galvanized, or copper, or steel. Minimum 5/8 diameter, unless it's a listed ground wire. If it's a listed ground wire, you can well, HEL. It takes into account the thickness of the coating, the copper coating or steel, and that will give you the equivalent performance of just a 5/8 diameter plain rod. Generally, stainless steel is used in some areas. The copper coated steel is the standard for ground electrodes. They hold up well. Stainless sometimes doesn't hold up well, depending on the chemical makeup of the soil. The plates, if you want to better plates in ground, it could be steel or iron, it could be copper, but that wouldn't have a long half-life. It's there, so you put it in the ground. The measure resistance, what's usually done is the so-called fall detection method. You inject current into the ground, and measure the voltage. When you get to the point here, you plot this point. This midpoint is what's considered the ground resistance. The code requires 25 ohms minimum, which is still a pretty high number. If you had a cell site or something like that, they would be looking for much lower ground resistances, and they would go to great lengths. There'd be a lot of electrodes in the ground, a lot of copper wire in the ground. Resistivity of the soil can vary tremendously. Talking with George earlier, Long Island, a good part of it is sand. And sand basically, it's like putting something into a glass insulator. So a lot of times, people think they're on the South Shore, they're putting ground on it, and then it's surprised that it's such a high resistivity. But it's not that surprising, because it's just put to a pile of glass. As I said, the code used to require 25 ohms or less, and if it was more than 25 ohms, you have to put in a second ground bar. They didn't require another measurement to get it for 25. So typically what electricians would do, and the contractors, but it's cheaper just to put a second rod in than to have this test on. You have to put the two rods in and change the code to adopt that as the standard. The two rods, unless you can show that you have one rod that needs to be less than 25 ohms. Excuse me, 2011. Okay, connections are very important. There are mechanical type connections. Some of these are listed for use in direct contact with soil, so we not have to make sure you're using the right one. And it's best to have it where you can easily access it and not have time to stay there the road you're playing. This is the mechanical connection that they're hammered on for one shot. Plants, you can use this one that's put on, it's done. But it forms a very, very good, what's called a gas tank indetermination between the multiple conductors. There's no gaps, there's no interstitial spaces to see go. This is a current connection that's not, you can see a lot of empty spaces. Eventually, you're going to have corrosion set in there. This is what a good compression connection looks like. It almost looks like a solid piece of copper instead of all the strands. But this is the best kind of termination. The exothermic welding, it's used a lot in industrial application. In the home application, it does generate a lot of sparks, a lot of smoke. The classic Cadwell mold, the graphite mold, and this powder here, and you have a little naive material, you spark it, fill it up, spark it, so boom. What you can use, the hands usually use one shot to buy them. If you only put in a couple of connections that they have ground much not design. The one shots to buy them and use them for what's left. And they can also be done remotely with a electrical means. It doesn't require any spark. One thing to be very careful, you have exothermic welding systems. The connection points have to be extremely completely dry. Any moisture in that, the minute the reaction takes place, the steam generator will throw the molten metal all over. Name bonding number, this is in your service panel. They can be one of several forms. It could be a screw, it could be a bus bar, a cable. In this case, you have this bus bar in the back that goes from the neutral bar to the ground bar. Your ground electrical conductor comes up to the neutral bar, and then this jumper connects the two bars together. If you have a separate panel, some call it a sub panel, technically it's not, or an additional building, you don't bond the neutral and the ground there together at that point. They only get bonded together at the service. So if you're running it to another panel, you have to run all the neutral and the ground and the line wires. You can't get fired, without it. If you have a separate main disconnect, then this is where your connection will be. This is where you have a connection here from over here over to there. And this green screw can also be the main bonding jumper now where it joins two bus bars together. Okay, if you have threaded and screw connections, you need at least two threads or, into the material, or not. A machine screw is, the preferred type. A machine screw, a thread cutting machine screw, so basically from here to here, you have a conventional thread. Here you have a tip that looks like a shaft. That's acceptable as long as you got two of these threads per gauge. Hex screws that have a drill point are not considered suitable, nor are sheet metal screws. Whenever you're running a ground conductor through ferrous metal conduit, it's important to bond the conduit to the conductor at both ends so you don't get a choke effect. Because then it'll feed the truck will be like a big impedance pump if there's a flaw. This is typically how you do, the bonding around there. But by this connection here, you achieve the same bond between these points. Okay, if you have aluminum or plastic conduit, you don't need to have that same bonding. It's just another way of making that connection to a pipe. You have both the termination and the bonding. This is something that violated. I want you to see a panel installed with the ground electrode conductor. The electrician's punching the hole in the bottom of the panel to conduct through it. And probably for 200 amp service or less, not a big deal, even though it's technically not compliant. But once you get into a 400, 600 amp services, the current flow is such that you get a inductive effect and fire and damage. But they do make a fitting that bolts up to the enclosure. The conductor goes through that is tightly bonded to it. And the larger size of the conduit, the cable and conduit, this is the kind of thing that we use. See, this is a bad practice that short end. This is connected, used for connecting a conductor to a water pipe. This is not generally for ground rods, unless it's specifically shown to be listed for that use. Anytime you have the reducing washers, you have to bond around the non-reliable path, and this is a super no-no. Having all this slack there, anytime you have a current flow of the conductor, the magnetic forces aside, that this will just be whipping around in the breeze, probably rip itself right out of the conduit. If you ever get a chance, sometimes the AD Chance company, we have some, before they had video homes of the safety grounds that the utilities use. The big yellow cables, like big jumper cables, and when those take a hit, they just dance all over the place. In fact, once they hit a wall, they're destroyed. They're no longer good because it removes the temporary operating, it removes all the properties. But it serves the purpose to prevent somebody from getting killed. Your body around meters to provide a continuity to the water pipe. The problem is each of these flange matches that yes, there's good chance there's no contact with the bolts, so you basically defeated the path by doing that.
Okay. Don, just a comment, go back to that slide. Very often those things are full of asbestos. Yeah.
Back in the day, if this is going to fight the fiberglass or one another rock wool, the insulation.
Hopefully, most of them are old.
Yeah, I mean, if you don't have an old building, you can tell the asbestos ones are usually it's been slathered on semi-nuclear.
It's like,
It's only a cautionary note.
Yeah.
Be very careful.
it's like a liquid slurry that they surround it and then put a cloth around it.
Yeah.
Like,
This is more technical. Like, as a matter of fact, today they have some much more finely engineered type insulation. Because insulation, just as a side of pipe insulation, is one of your first barriers against, corrosion under insulation, which, your pipes can rot away under the insulation and will get condensation. Okay, this is a point that, number one, you can't use your gas pipe as a ground electrode. But if you have a gas pipe that connects to something that could energize that piping, it has to be bonded with the service tank. Especially if it becomes a problem when you have the corrugated stainless steel tubing that's used for some of the newer installations. It looks like a glorified appliance flag. Now the problem is if it's not bonded and you get current, take a hit, the arcing can melt through the metal very thin. Then you get a leak, gas leak, and the arcing ignites and go boom. So the corrugated tubing, if you have it, the bonding can be done one of two ways. If the appliance has a three-wire ground, like the gas wire and close, that provides the both required ground connection. If it's something else that doesn't provide that, then you have to put a piece of 3-inch piece of pipe on the entry point and bond for that. Now, even though there be some manufacturers will claim that the tubing or the fitting can be used for the connection, it's up to your local utility. The legislative check, the national grid rule books still show that this, you have to go with the separate, stuff, not on the tubing or on the nut.
Hey, Don,
Yeah,
in an apartment building, is that bonding usually taken care of down in the utility room, or do you have to deal with it in each apartment?
well, if you have a gas appliance like a stove, and then you generally have some electrical thing associated with the clock, light, and so forth, and as long as that's three-wire grounding plug, that establishes the bond you need. If you didn't have that, and you had some other kind of appliance, then you'd have to make sure that they could provide that bonding connection. Okay. This is right from the blue book. Okay, another thing that can be confusing is type MC cable. Type AC cable, which looks like what used to we call BX, is one kind of construction very similar to it is MC or metal clad. The difference being that type AC cable, the armor is always considered acceptable as a grounding conductor. Type MC cable may be acceptable as a ground conductor or may not, and it will be marked to indicate that. AC cable always has a drain wire, a little drain wire inside that binds those little spiral sections together so you don't get a choke effect. MC cable may have it, may not have it. And again, it'll be indicated usually service printed what it's good for. The main difference is that AC cable is very strictly limited to the number of conductors and the size of conductors. MC cable has a much wider range of quantity and sizes, gauges of wire that can be inside. The other difference, there's a terminating AC and MC cable that is slightly different. AC cable, the connecting have to, before you put the armor into the connector, you have to put a little plastic bushing in there. MC cable, the terminations, the connectors are provided basically interval that you don't have to use to go right at, bushing. Okay, again, a few more definitions. The grounding conductor that's intentionally grounded, neutral. The equipment grounding conductor is 3-wire that provides that, effective grounding together if needed. And of course, the ungrounded conductor is, those are the same as this. Okay, and there's the AC cable, there's that drain line. This does not go into the electric box. This is just get folded back. The MC cable on this case does not have a drain wire, so would not, the owner would not be approved for it. But what they can do, they can have a green conductor there to provide the ground. Yeah, this is the AC cable, determinations that drain wire can just put back either on top of one of the, but usually they put it on the over the bush. Pull it out, box. The grounded conductor are usual, we configure different ways. The only thing, the key point to remember is sometimes you have what's called a highway delta, orange light delta, goes by many names. When you have a delta system, where you have the 240 volts plus each phase, and then you got 120 volts to this midpoint of this phase. If you go around now, between this point and this point, the neutral, and you have 20 volts. If we went from here, now you're going to have like 43 volts, which a lot of equipment wouldn't necessarily be happy with. Usually there's an orange conductor cover with covering on the highlight, so you don't make that mistake. It's not seen too much in residential, unless you're in a apartment building next to a commercial area. Okay, just a bit of trivia, the major argument to the ground can be down or up. And you'll have people who swear that it's a code requirement or one or the other. There's nothing in the National Electrical Code that specifies that. However, if you commercially install into the system and the customer specification call that, then you would have to rely on the way of life. The receptacle grounding, anyway, you have a metal or plastic box. If you have a plastic box, you have a separate conductor. Conductor comes to the receptacle, the green screw on the receptacle. If you have a metal box, you have a conductor anchored to the box, and then anchored to the outlet suitable has a little contact point, and it can be considered the ground next to the yoke. Okay, GFCI used to be in a few places now, pretty much bathrooms, garages, accessory buildings, outdoors, all spaces. And there's very few places that do not require GFCI. With the current 2017 code, it's not required for a refrigerator or receptacle outlet that's a dedicated single circuit. That will change with the newer codes. There's always been an objection to that. You said, what if trips and the food goes there? Well, what if it's not there and you put the refrigerator and you stove at the same time and the electric food? This is what's inside the LEDs. A lot of electronics. What do we know about electronics? They fail. They have light. The mortality, the end of life, the advanced number, everything's fine and in between. But traditionally, early GFCI did a great job, but there's no way of knowing really if it was still good. Because of course, everyone presses the test button to make sure that they're working, which is technically required. Okay. The new ones. The first generation new construction that the self-testing, fail safe, and it would trip out, knock it out if it's not functioning. The new ones actually, do a very, frequent check, and it will enunciate, every normal enunciation if it fails. So you don't have to worry about food falling out. You won't get home with trips. And somehow they have GFCI breakers, and just again, GFCIs, the Class A 4-6 milliamp trip levels for personnel protection. Ground fault protection for equipment is what you have when you have marinas and things like that. Trip levels that are much higher. Then to protect equipment from fall, not the personnel.
Hey, Don, is it better to put a ground fault breaker at the service panel or at each individual end of a run receptacle?
There are advantages to both. There are advantages to both. There's only one place to deal with it. The problem is that it goes to different places. You can individually ground fault protect one area of the room and it won't trip out the other. If you failure to have a breaker, if it trips, that area. So, when GFCI breakers and receptacles first came out, there was a problem with radio frequency tripping. They already solved that problem. Now, the so-called AFCI, there are full circuit developers. Initially, they had the same kind of problem. At least one or two of the manufacturers were very receptive to the fact that they could make it correct it so it wasn't RF sensitive. So it shouldn't be as much of a problem as it first was.
Okay, Don, just 2 points here. Point one, if you have the ones mounted in the panel, you have twice the number of wires inside that panel. If you have a very dense panel, it's going to be very difficult for an electrician to wire them properly. Simply because you have to bring out the neutral wire, which usually doesn't show up in that panel the same way.
The panels that would accommodate this GFCI breaker
Maybe much physically
are
larger.
bigger.
Right.
Okay. And a lot of them, you can't fit these into an older panel.
Okay, and the second point is that the way that all of these things work is with the differential transformer. They have little toroids built into them, and they basically subtract inside the device that's the ground fault interrupter. There's 2 toroids, all right, and there's a sense wire in them that senses whether or not there's a magnetic field, because when it's not a ground fault, the magnetic fields cancel each other. And the ground fault wire, the trip wire inside there, doesn't have any current. However, if there's an unbalance, i.e. there's a ground fault someplace, the 2 transformers in there have a generated current, and that's what turns on the electrical circuits to say we have a problem and let's handle the circuit. So it's actually a differential mode transformer that's doing the
very
sensing.
much like using the light bulb to sync 2 generators.
It
sounds like it.
That's just phasing, that's getting the phasing right. But it also explains why be protected against ground fault by the GFCI. But if you put yourself on the line in neutral, all bets are off.
Well, there, because there's no
differential.
right.
Same. Okay, why do you have if you have a fault, say a motor. If there's no grounding, and you're touching the enclosure, you become the path of the ground, sitting on a slab of wet concrete or dry concrete. Okay, with a grounding conductor, and a lot of people say electricity takes the easiest path. It takes all paths. So if you have a grounding conductor, there's a fault, and you're touching it, until something else trips, you will feel a tingle, but it won't be sufficient to kill you. If you provide an effective grounding path, electric current gets that fault. Same thing when you're in a substation, say, they put these big grids in place because if you have a fault, you can have these gradients, voltage gradients And, just standing like this with 2 feet on the ground, you may put your feet across enough voltage to generate fatal current. So if you're in any kind of installation where you, all of a sudden the hair on your arm gets up, you get on 1 foot and just hop as far away as you can. And it sounds crazy, but that's actually a recommended practice, for electrical safety. Now, if it's any equipment, there's a pole there, and you're standing under to provide the path there. Typically, they'll have mats, conductive mats, and these things to even out the potential, so it's not as great. If you want to, when you're laying out your grounding determinations, you don't want to have it where you disconnect, no daisy chaining, so when you take out 1 wire, 6 other wires are floating in the breeze. They should all be secured separately. And we want to make sure you provided that equal potential bonding there. Very, very important. Okay. Discrepancy in performance, the tying the radials for an antenna together doesn't make much difference. The size of the wire doesn't make much difference. It's again more better. However, since it's all going to be bonded to your other grounding system, it will have to share some of the current load. So you want to make sure the wire is thick enough, heavy duty enough, and some current, and it will, by having your radials tied together in the fringes, you're creating now a better potential map for the area. You even out that peak, slides it out, so you have less chance of step retention. Okay, the question was, what does the electrical require aperture radio installation? Keep in mind, most of this applies to wire antennas and open wire fuse. Why it's important is that you're embroiled in a problem, like you have a neighbor that doesn't like a tower, things like that. That happens occasionally, but really not. Some people consider nice.
What's wrong?
Someone can come in and say, well, you're not complying with the electrical code and create a whole bunch of problems. So just to give you some of the things they talk about, the and discharge units, sometimes what they're asking for is not commercially available. And an intended discharge unit is not like an arrest, except the load and discharge the charge that comes up, it goes up with a light electrical storm, something like that. The old days, twin reason everyone had that little red plastic thing that was filled with this horrible tar coming down, just like a resistor. You just trap the water pipe and run the thing to little two watchments. That was a big discharge device. Okay, Article 10, the NEC is available online for free in a read-only mode, and it's a real clunky interface. What happens is the NFPA makes the money for some standards. Since the NFPA 70 has been adopted by certain legal bodies, OSHA primarily, they're required by law to make it available to people at no charge. So they have a very clunky interface, but if you're looking for just a particular section that it works, you can cut and paste on besides. But at the NFPA site, and you work your way through, and you have to set up a no-cost account, but then you can log in and download any of the students, whether it's the NEC or anything else. Okay, most of it, we talk about wire size, length of the antenna, separation. A lot of it doesn't apply to antennas that are coax because they consider the metallic shield as being enclosed. Just a lot of stuff primarily would affect open wire feeds.
Just on that screen two back, it made reference to the rolling ball method. What is that?
Oh, we'll get to that. I just started later.
Oh, okay.
Okay? Try to zip through here. Now, yeah, clearances, the rounding. There was space regarding, you know, it's not good practice to be running your clean line in close proximity to the power lines. It actually gives you the minimum spacing, but you really don't want to have it anywhere near it. Material requirements, and again, this is probably violated a lot too. It's amazing, when we first started on the radio, a friend of mine had a 500 foot, 1,000 foot spool of 18 gauge, insulated wire, and we were all making 10-meter vertical dipoles with that. It worked. Okay. And again, you know, if not properly grounded, shielded cable, then and a discharge units, generally open wire feeders. Transmitter requirements. Not too many people build from scratch anymore. But if you did, and there was 150 volts, they have to run interlocks. Now, if you have an commercial piece of equipment for it that still has those little things that glow, you have high voltage, you don't have to worry about it because the National Electrical Code does not apply to completed devices as long as they are in themselves listed. So if you have a radio, it's CPL or UL listed, you don't have to worry about this section. It's considered in compliance. So you don't have to look further into a previously listed device. And code excerpts, again, nfpa.org. And another great source, and we're just touching the surface and grounding. There are people who devote a whole career to grounding. And a very interesting field, and the whole history of the Uber grounds and the ammo storage sites and stuff like that was developed to prevent things from going boom in the armament area and store munitions. So Mike Cole, his site is select forums, they can check grounding, NEC, there's a lot of really good information, but a lot of it is also, you know, it's kind of like Wikipedia, you know, it doesn't refuse the print. Yes.
So I guess probably a lot of us dipole, so we have the coax, 6 feet, 3 feet jumper goes from the back of the rig to an antenna tuner, and then the back antenna tuner, it's got a valve built into the tuner, so it just comes out as two terminals, and then you connect the ladder line, let's say, to those terminals, and then you bring them outside your house and you put them in the trees, and you map your dipole. So what kind of grounding do you need? Actually, we'll ground into the house ground.
Open wire feed.
It's not really open, but it's got some plastic on it, you know.
Yeah,
It's coax versus twin lead. Twin lead is open wire, coax is not.
ladder line, any of these, you do have to provide some type of protection. Generally, the easiest way to do it is to put like spark gas, so that if there's a higher than certain potential that before it comes into the house, you have a spark gap, bond that to the connection to the ground. And typically what you'll have is if you have an entry point for your antennas, coax, ladder line, rotating cables and the like, you bring them all into one box, then you have copper bus bars, you terminate the grounding device, the surge protectors there. So everything then that gets connected to your ground electrode for your cam station, and that in turn gets bonded with a 6 gauge copper wire service ground electrode. Anyway, the whole the site has a lot of information. Just beware that a lot of times if you have 12 people, you get 12 different answers, with some very different than one another. So like talked about the best way to just that and just again, typical very crude illustration of, bonding things together, when it comes to patch. To cut briefly on lightning protection, the key point in lightning protection, you have air terminals, which is typical copper terminal, it's mounted on higher platforms. And then we have the emergency radio station, typical, air terminal. Without mentioning where this was, the interesting thing is this installation was not very well protected against lightning. And yet it never got hit, never got down, because some areas are more prone to lightning strikes than others. I know I worked with someone whose mother's house was a low ridge, no antennas, no nothing. Big trees all around, lightning bolt right through the roof, down into the insulation, the rafters in the kitchen. Took out a lot of equipment, fortunately, started fire. The lightning will go where it wants to go, which will get us to the next topic, the zone of protection. You used to say that zone of protection or double zone of protection. That has been disproved, but what is used now is so-called rolling wall method. Okay, you have this 150-foot radius wall, and the space shaded where it contacts together. That if the tower is protected, then everything in that is protected, even if it doesn't have a connection. And this was, developed by people with long range design. They came up with this empirical equation, kind of fitting the points to the results, and but the bottom line is, lightning's going to do what it wants to do. There are photos of lightning strikes hitting the Empire State Building significantly down to the top. One based on folklore would assume, oh, now it's going to hit the top, all the antennas and everything. It's going to find an ionized air, and a lot of different things can cause that. It can be particulate matter. We don't live in an area with air that's perfectly pure. There's smoke, a lot of things. So the best you can do is just take due precautions, but keep in mind that it's got to mind all of its own.
Yeah, just one comment here is, it doesn't necessarily come from the cloud to the ground. It can go the other way.
Yes, well, it's actually both, you get a streamer from the ground up and the cloud down. And that's what causes, because now as that streamer comes up, it's ionizing the air around it. As the other one comes down, it's going to find this ionized path and bingo, it takes a hit. Okay, to summarize, ground rod should be 1 to 2 times the length, so the depth of that length, even though that's way in excess of what the code requires. If you have to put in more ground rods, go longer instead of more of them to get more bang for the buck. And just a side comment about codes. The National Electrical Code is that's the basement. That doesn't mean that it's perfectly safe. You can always do better, and sometimes it's advisable to do better. Both from the point of view of both from the point of view of safety and avoiding future difficulty. Because sometimes it's like you use the cheapest device, something that's more common, cheating out on your level of protection. For a while, I was teaching a code class, and someone came close. One class was all electricians that were in the trade working. And one guy said, well, if I just do it meets the code, shouldn't I be safe? I said, well, yeah, if you go to court and you can sue and show that you met the code. But in the meantime, you just paid for an expensive lawyer. You took 3 days off of work. Is it worth it when you can knock you off in safety for a few pennies and not have that problem? So it's the code is starting. Just like this is the starting point. Some of you will be moved to delve deeper and deeper into the ground. Like I said, the light bulbs site is a good one to get started. Some references. There are other references Anyway, ground resistant, the lowest possible, not only in homes. Ground is the low point of the earth, table not before into the building. You don't want to wait until the surge is in your house. You want to keep the traffic out of the doors. Ground bond edge bonding things within 6 feet. And avoiding gas piping. Don't want to have any kind of a potential difference that could cause an arc near any of the gas piping with duct. If you have a slight leak, it can create a problem. Okay, this is the key point. It's no sharp ground covers. Yeah. And generally put your conductor so it's pointing down. It's more from a safety point, because someone at some point is going to be inspecting that to see what shape it's in. You have loose strands of copper sticking up. Somebody, it's like the phone guys. If the guy left the tails on the zip ties, people would throw them out. Because eventually, well, you leave a sharp edge and cut it diagonally. You want to do things to not create a potential problem. Okay, bonding everything together that's within an area that can be touched electrically or physically. Some of the stuff that a lot of polarized plugs, some still do. They have a wide blade. That's fine, except two things. One, the assumption that the house is wired correctly, that the wide blade is in fact a neutral or grounded conductor. That generally is the case, but not always. And if it's an old house that has an old receptacle, from plugging things in and out for so long, that they're both the same. They both fit the wide blade. It's not as much of a problem now as years ago when you had the tube TVs, you had the direct hot chassis, you had radios, AC/DC radios that had hot chassis. That became more critical then, because if someone, the knob is missing, so you stick a screwdriver to adjust it. But it's something, you may have small equipment. Some people collect old radio equipment. And
If it's plugged in wrong, you can feel on the surface of the chassis, it feels something's going on. And when
You're
you turn
brave
it
enough
on
to
the
touch
other
it.
way,
if it's a hot chassis, yeah, you will. You'll be better as well.
Just a cautionary note. Many years ago, I was working for Telecare, the Catholic Church's television system. And one of the crazy things I was responsible for was television receiving systems in just about all the schools, over 80 schools that had television receivers wired with the cable TV setup. And I published every year a list of acceptable TVs, which was never followed. The parents' clubs got together, they found some dealer, usually an enthusiastic parent, who would find the cheapest possible set that they could donate to the classroom. Many of them did not have power transformers. Many of them had hot chassis. And the only thing that was keeping the students in the school or system area terrific was a chassis that featured plastic knobs. God forbid that the kids steal the knobs and the teacher walks in there with a pair of pliers to change the channel. We had several incident cases like that.
Where you have the hot chassis says, one of the things that is UL listed, one of the UL requires that the knobs, if they're relied upon to close that access, they have to be activated. Unfortunately, they accepted that if it was glued in place and the glue was shown to have a long lifetime, they would consider it acceptable. I know for a fact that a assembly is a little two pots with plastic knobs glued on one of the Sony bond materials. Passed all the aging tests, heat, humidity, cycling, was fine. But about 15, 20 years later, I needed a little bracket. I said, put those little pots on that TV. take it, I go to grab it by the knob, just pull it right off. Adhesives, plastics, you know, we rely an awful lot about the composite materials, but we don't really know about a lot of long-term lifetime. I look at all these laminated utility poles, but,
Well, if it electrocutes you, there goes your lifetime saving.
yeah. Anyway, okay, and you put in a grounding system, you also have to check on it. So the easiest way to make like a little well, where you can, you know, that piece of PVC with a cap on, you can look down, making sure everything is still in one piece off and dig it up and everything. Okay, this is something you can find on the internet. With Bill, I have both. That's really good. A lot of good stuff, typical military, it's probably some of it's old, but again, a good starting point. This is like kind of the Bible in radio communications. Keep in mind, this is for very expensive installations that can't afford to go down. So the things that are specified are well in excess of what we normally do for a home station.
Right, put your minds at ease. We use that particular book on our repeaters. When we set up our repeater stations, that book is the technician's guide. I know that the Steves have sent that book to me.
It's a
So,
good book.
yeah, it's a book.
Yeah.
It's good.
Any questions? And then if you think of questions after this, you know, sometimes it takes a few days to get to it. Lately, it just seems like an email, just, you know, multiplying and which way. But this is like an introduction. Yeah. Key things to remember: you want to have potential bonding. You want to have good ground electrode systems. Most importantly, you want to bond your ground system to the service ground. One question that comes up a lot is, okay, I got my tower. Why do I have to bond that to the service ground? So I got 3 ground rods around it. It should be fine. Again, you have the coax coming in. They have more than one piece of coax. Now you have connections that could be bringing this voltage rise as a hit. Things are going to be in different potentials. Now, if it's 150 feet away, yeah, but it's not going to be able to carry much current because of the inductive effects of the length. But to equalize potential, it's important. So just something to keep in mind. And the bottom line is the National Electrical Code doesn't require that structure has to be grounded and bonded back to your service ground. So, again, will that ever come up? Generally not, unless there's an insurance claim, you get a fire due to an electrical storm, and your tower isn't on the ground, isn't bonded back to your service ground. Insurance company could come in and say, oh, you know, I really feel bad for you, but tough. So, I hope no one's here from the insurance industry, but they're in business to not give away money. So anything they can find to avoid paying, they will. So some of these requirements are kind of out in left field, and I don't think most of the AHJs, the authority having jurisdictions, are that well versed in the Section 810 for this. But where it really would become a problem is if you're embroiled in like a tower problem, where you're going to the zoning board, and depending on how good a lawyer they have, you know, the question could come up. Any other questions?
What would be the correct size ranging from the tri-light and generally move what size bound light is the most appropriate and should be
It can be bare or insulated, generally copper, for that, 8 kV minimum. Biggest you can afford is usually better. The one time when you're bonding, when it comes down, say you have a dedicated ground off of that, then bonding that to your service ground, that has to be a number 6 copper.
for what gauge wire do you use?
The number 6 for bonding your ground electrode to the service ground, but it would be number 8 from the
8 coming down, 6 to
your ground.
Just a comment on those two. I've had several run-ins with inspectors. They're very picky about the color of that wire. If it's uninsulated and bare, that's fine, but they really want to see a green colored insulation on those things. And if it's not green, then they won't approve it. Honestly,
It can be green insulation, or you can apply like green tape and heat shrink clear tubing over.
I should be able to, but that depends on the inspector.
Yeah, and you gotta remember, the AHJ has the final say. He's like God.
Right.
So, and I mean, there's usually procedures for complaining and taking issue. God, have you ever want to get anything else inspected, you know? So, and it's different. If you're an individual and it's a one-shot thing, you take it to the max. If you're a contractor,
Yeah,
you
this
want
was
to
her college job.
if you're a contractor, you want to keep on the good side of the inspector.
If you're using a bare wire, you have to keep it off when you insulators or can lay on the roof.
It can lay on the roof, but generally, you want to have it secured, which is going to require some kind of standoff. Because again, when it takes a hit, it's going to be moving all over. You don't want to have like a loose length of, the forces from short circuit power are just beyond imagination. If you haven't seen it, it's just beyond imagination. Many years ago, Lilco's had an issue about, these monopole transmission towers you see running along the length of the island that it's going to connect to Shoreham and Jamesport. But those are just slip fit connections, the sections. There's no, it wasn't bolted together or anything else. And there was a concern whether, because they would attach the safety grounds to the little stud on the pole, whether it had an effective ground path. But so they set up a test behind the pixel facility. They had, I'm trying to think, it was 6 or 8 750 NCM copper cables attached to a copper plate. And then they attached another set of cables. They had it so they could energize this with their full substation voltage. And when that thing, on the split second before they detected the reline and shredded, that thing just moved about 3 feet. And if you're going to try to bend conductors that big, that's quite a feat. You have to use a pipe or something to get it bent. Very risky.
I've seen film clips of a downed power wire. It's just clipped. It's just a wire that stops. And it was sitting in water and it was bouncing all.
Yeah, that's why, some of you see these reports on TV, and they'll go, and they want to get close so you hear all this cracking and stuff. It's so good, because that can jump around and you can cry. But, and only that, it's like the one time, where I used to live, the phone company could find the underground line, which is totally shot. So we put, telephone between every house, these bundles and bundles along the pole line. And in some cases, it moved down, concrete truck went by one day. Now that thing is a steel messenger. So it sags the wire, starts stretching like a bow, and then it lets go when it finally snaps. And the loose end came back and wrapped itself around 3 times around the parked car. And the woman comes out to use her car, to see this, and she's freaking out. I wasn't home, I come down the block and I see police, some kind of police, cable vision, phone company, Wilco, they get called out of the world. I mean, they didn't know, he didn't know that this was just a telephone wire. And so he did the right thing, call the utilities, get down to it. So you also have to be careful, what the problem is meant to be improvement is reliability. What they call tree wire. Your primary, your 6-gauge primary 7,000 volt distribution. You sell it with bare top. But a tree limb falls on in the winter, or if there's too much ice, it comes down. The tree wire is a very thick polyethylene insulation. It's not meant for electrical insulation, it doesn't provide sun, but it's not meant for mechanical protection, so the wind, they don't support the wind that operated in the company. The problem is when it does come down, you'll end up the conductor close to the ground, it's just starts to arc and bounce and dance around. So I think if you go there and sometimes it'll generate this tremendous arc, lights up the night, dark. Burn a hole to the roadway, the front yard, whatever it is.
I've seen that.
If it happens to be where you still have some metal gas pipe, you know, then it goes down that far. It's electricity can be that next up. Anything else? Okay, thank you.
Okay,